right now I will be sharing my desktop or my screen with you. So if you cannot see my paint, please tell me, because otherwise I'll continue. Okay. So I think we're ready to start now. And yeah, welcome. I hope that this will make it a bit easier for you to do these chemistry calculations afterwards. That's the reason why we're doing this today. So today we will be discussing the chemistry calculations, and you know, this is a central. This is a tool that any chemist on any level uses, from our level and up to professors sitting on universities doing calculations before they can even start working on any project. So it's a quite important tool for any chemist. So this is the reason why you really have to know how to do this. And it's not a simple method we're using. It is quite difficult to do. So I understand why some of you are struggling a bit with it. And before we get started, let me just tell you that you can always just unmute your microphone and just ask me to repeat something or to tell it in a different way, because hopefully it will be a lot clearer afterwards once we're done how to do this. So please ask questions when we're going. You can just cut me off and just ask me to tell something again if you still are having troubles with it. But I think we should get started now. So I have just written the equation for the respiration reaction. So this is the reaction that is going on inside all of our bodies right now. We are digesting sugars to form carbon dioxide and to form water. This reaction gives us energy, and that's the reason why we can think and why we can move our muscles. And it also provides energy for a bunch of different chemical reactions that require energy to proceed. And the respiration also needs air, so it needs dioxygen to react. So we have two reactants now. We have the sugar. This is a glucose molecule, and we need dioxygen, and then we can form carbon dioxide and water. And I haven't put any states on the molecules because that's not central today. But for example, when we are dealing with a problem like this and we are told that there are, for example, it could be 0.1 grams of glucose. And we are asked, and we're asked how much carbon dioxide is formed. So when you're asked to determine how much carbon dioxide is formed, it's always mass that is asked about. So we need to figure out what the mass of carbon dioxide is. I'll just delete this. And we know that we have 0.1 grams of sugar. So the first thing that you do when you have a problem like this is that, so is Lærke back on? Can she hear anything? Can anybody else hear me? You can just write in the chat or something.
Yes.
Yeah, okay, cool. So I think I'll just continue because I think there's an upper limit of how long I can keep going with this recording. So when you have a problem like this and you know the mass of either one of the reactants or you know the mass of one of the products, the first thing that you do is that you balance the chemical equation. So to balance this chemical equation, we know that there are 6 carbon atoms. So we'll have to put a 6 here as well, because we need to have 6 carbon atoms on the product side as well to have conservation of mass. And now we can see that there are 12 hydrogens in the reactant as well. So we need to have 12 hydrogens on the product side. For each water molecules, there are 2 hydrogens. So we need 6 water molecules to have 12 hydrogens in total. And now there are 6 oxygens on the reactant side, plus 2 from the dioxygens. That's 8. But we have 6 times 2 oxygens on the product side and 6 more oxygens from the water. So that's 18 in total. And we have 6 there. So we need to have 12 oxygens from the dioxygen. And if we put a 6 coefficient there, it adds up to 18 oxygens on the reactant side and 18 oxygens on the product side. So now it's balanced. The next thing that you do is that you write mass, and that's in grams divided by grams. You write molar mass, and that's in grams per moles. And you write amount of substance, N, divided by moles. So if you cannot read what I'm writing, then please ask me to say it out loud or write it a bit more nicely. So now we have our table that shows the chemical calculations here. And after we've balanced the chemical equation, we put in all the different things that we know. So we know that we have 0.1 grams of glucose. So that we write there. Let's make it a bit bigger. There we go. So we have 0.1 grams of glucose. And we also know the molar masses of all the different compounds in the equation, or in the chemical equation. So we need to determine the molar mass of glucose. And we know that there are 6 carbon atoms, so that's 6 times 12.01. 12.01 is the molar mass of carbon. And we add that to, we add that to 12 hydrogens. That's 12 times 1.01. And that's also grams per mole. And there are 6 oxygen atoms as well. So that's 6 times 16.00 grams per moles. And that gives us let me see, I haven't done the calculations. So that gives
mass.
Yep.
But isn't it 12 times 1.008, or did you just round it up?
I just rounded it.
Okay.
So that yeah, you could also use 0.008, or sorry, 1.008 for the molar mass of hydrogen. But yeah.
But it's just to have the same significance figures?
Yeah, it's just so all of them have 2 decimals.
Okay.
Yeah.
Okay, thanks.
So this gives 180.18, and that's also in grams per moles. And for dioxygen, it's 32 grams per moles. and you have to remember here that you don't include the coefficient in the molar mass. So you only, I'll just put a line there. You only just take the molar mass of a single compound. So of a single formula unit. So that will be of one dioxygen. So this coefficient here you include, but this you do not. So the 6 you do not include in the molar mass, because that just shows that there are 6 dioxygens, but a single dioxygen atom is the one that we want the molar mass of. So that's 2 times 16 gives 32. And carbon dioxide is 12.02 plus 2 times 16.00. And that's grams per moles. So that gives 42.01 grams per moles. So I'm just going through this a bit quickly so that we can get to some of the confusing parts. And for water, that gives 18.202 from memory. So that's 2 hydrogen atoms and 1 oxygen atoms added together. We ignore the 6 here, and we also ignore the 6 in carbon or in front of carbon dioxide, because that does not show what is actually inside the molecule. It just shows how many molecules are there, or the reaction ratio. Just delete this again. Okay, so now we're ready to do the chemistry calculations, and we want to know how much carbon dioxide is being formed. We can also calculate how much dioxygens are being consumed in the reaction. So to find the amount of substance is equal to mass divided by molar mass. So that will be equal to 0.1 grams divided by 180 grams per moles. So that was the number here and the number there that I used. Let's see. So that will give us 0.1 divided by 180. So that equals to 0.000555, and that's moles. All right. So now we know the amount of substance of glucose in 0.1 grams of glucose. So here is for the tricky part. So now we have to calculate the amount of substance of dioxygen, for example, that is being consumed in the reaction. Just try to make a nicer scheme. There we go. And for this, you need to know what the ratio of the reaction is. So if we just go there. So the ratio of the reactions are the coefficients that is given from the coefficients. Ratio of reaction. So that's, here there's an invisible 1 to 6 to 6 to 6. That's the reaction ratio. So here I just look at the coefficients of the different compounds in the reaction. So the meaning of this is that one glucose molecule reacts with 6 dioxygen molecules, so that's the 6 there, to form 6 carbon dioxide molecules and 6 water molecules. So that's the meaning of the ratio of the reaction. You could also translate it into amount of substance. So if you had 1 mole of glucose, you would need 6 moles of dioxygens to react with the 1 mole of glucose. And that will in turn form 6 moles of carbon dioxide and 6 moles of water. So that's the meaning of the ratio of the reaction. So if we go down here again, whoops, down to this part here. So if I just draw a line here. So we know that the ratio of the reaction between the two reactants is 1 to 6. So one glucose molecule reacts with 6 dioxygen molecules. So the ratio, so the amount of substance of dioxygen has to be 6 times larger than the amount of substance of the glucose. So I can write here amount of substance of dioxygen. Unfortunately, I cannot lower these numbers here, so you have to live with that. That would, of course, that's a requirement normally. But it's 6 times larger than the glucose molecules amount of substance. And the way to calculate this is that you put, let's see if I can do this properly. Yeah, so you put 6 times 6 moles of O2, and you divide that by 1 mole of glucose, C6H12O6. So paint wasn't the best option, I can now see. So you divide those two, and you time it with the amount of substance of the glucose, C6H12O6. So is this clear what I'm doing here? Or should I try and explain it again? Yeah, so it will be recorded again. Yeah. Okay, so I'll try to continue. So let me just write again. So that will be equal to 6 divided by 1, because that's the ratio between the oxygens that we need to figure out. So that's the 6, and the glucose that we're transferring from. And so 6/1 part times 0.000555 moles, and that is, sorry, that's equal to, now I just need my calculator, 0.0333 moles. So now we have determined the amount of substance of dioxygen from glucose. And from there, just need to find my eraser, there we go. From there, we can calculate the mass of the dioxygen. So the mass of dioxygen will be equal to the molar mass of dioxygen times the amount of substance of dioxygen. So that will be equal to, let me just make it a bit nicer. There we go, to 32 grams per moles times.
Can they hear me?
Sorry?
Oh, okay.
Times 0.00333 moles. And that equals to 0.1 grams of dioxygen. So to react 0.1 grams of glucose, there needs to be at least 0.11 grams of dioxygen in the reactions for the body to respire, to do respiration of 0.1 grams of glucose. Yeah. These two, this amount of substance here and the amount of substance there those are the equivalent, those two those two amount of substances are equivalent to each other. So those are the equivalent amounts, and that's because the ratio between the ratio between the amount of substance of glucose divided by the amount of substance of dioxygen equals to 1 to 6. So this fraction here, if you were to divide those two numbers, that would give you 1 divided by 6. So that's equal to the reaction ratio. That's the meaning of the equivalent amounts. So equivalent amounts are, you have equivalent amounts when the reaction ratio is in the same when the amounts is in the same ratio as the reaction ratio. So the one up here. This one, that will be the equivalent amount, and we can also find the equivalent amounts of the product being formed. And the way to do this is by transferring the amount of substance of glucose to carbon dioxide. And we can see from the ratio of the reaction that is 1 to 6. So the amounts of carbon dioxide needed has to be 6 times larger than the amount of substance of glucose. So it's the same ratio between glucose and carbon dioxide as glucose and dioxygen. It will be the same ratio, so it will be the same amount of substance. So I can write here that the amount of CO2 is equal to 6 moles CO2. Oops. And just make it smaller. That has to be divided with 1 mole glucose, C6H12O6, and let me just get this one, times the amount of substance of glucose, C6H12O6. So this is a calculation you need to show every single time you're transferring amount of substances. And it will be equal to the same number as of dioxygen, so this number here. So this is the same calculations for carbon dioxide and dioxygen, because the ratio are the same ones, 1 to 6 and 1 to 6. So now we are almost there. So now we can put now we can determine the mass of carbon dioxide. So that will be equal to the molar mass times the amount of substance, and that is equal to 44.01 grams per moles times 0.0333 moles equals to, and I just need my calculator now, 0.15 grams of carbon dioxide. So, and we don't have to calculate water today. Often water is not that interesting to calculate, because this reaction actually happens in water, so there will be plenty of water. So that's not interesting for today. But of course, sometimes you can be asked for it. Okay. So this was chemical calculations with equivalent amounts. Are there any questions for now? Do you want me to repeat anything?